Hello, my name is Niamh. I am from Breakthrough Maths. Welcome to this instructional video on how to prove that if three parallel lines make segments of equal length on a transversal, then they will also make segments of equal length on any other transversal. What does that even mean? Okay, first of all, a transversal is any line that transverses or crosses another line. Okay, so if you have a look here at a diagram, these black lines here are three parallel lines, and our blue lines cross our three parallel lines, therefore those are the transversals. And this proof says that if you've got a line like this, okay, a transversal, and it crosses three parallel lines, and when it does so, the parallel lines split it into equal segments, okay? So the way it's split here between A and C is equal to the way it's been split here between C and E. And if that is the case, then all we're trying to prove is that any other line that crosses it in any direction in any way will also be split into equal segments. It will also be split equally. Okay, so this proof involves a construction. I'm going to show you how to build this diagram I've made here, and then we're going to do a small mathematical proof based off this construction. So let's start with the construction. Okay, so the first thing I'm going to do is I'm going to draw three parallel lines. So I'm going to show you how to construct parallel lines. Now I also want them to be equidistant apart. I want them to be equal distance from each other. Now if you were asked something like split this line segment into equal parts or something, you should do this very, very accurately, okay? We're going to do it in a less accurate way, but that's okay. For this construction, it doesn't need to be perfectly accurate, that they're exactly equidistant from each other. So I'm just going to use my ruler to do that actually. I'm just going to measure it out. So I'm going to do one here, I'm going to do another one 3 centimeters later, and I'm going to do another one 3 centimeters later. And that's okay. I'm just going to, when I start doing my parallel lines, I'm just going to do those through those points, just so we have them roughly equidistant apart. Now, so I'm just going to draw a line through my first dot. There we go. Now the next thing that I'm going to do, guys, is I'm going to put my set square exactly on the line that I just drew, okay? I'm going to put my set square exactly on that line. And when it's exactly on the line, I'm going to put my ruler alongside of it. Okay, so the set square is exactly on the line and the ruler is set alongside of it. Now, and then I'm going to run my set square up along my ruler until I reach my next dot that I'd like to put my line through. And again, now I have my second parallel line. Okay, same thing again. I'm going to run my set square up my ruler up to the dot that I drew before. And now I have my third parallel line. There you have it, guys. We've got three parallel lines, roughly equal distance from each other. And to show that they're parallel, we mark that by drawing an arrow on each of the lines. And that signifies that these lines are in fact parallel to each other. Now I'm also going to label the lines. I'm going to call the top one L, middle one M, and the last one N. Okay. I'm now going to draw my transversal being my line crossing my parallel lines, okay? And I can pick it just at roughly any angle. Let's do it at this angle. Here's my transversal line. Okay. And I'm going to label this line T. Again, guys, this will all be in pencil for you. I'm doing it in pen to make it a little bit more clear, okay? Now I'm going to draw another transversal. Again, doesn't really matter where. I'm going to pick here. And this time I'm going to draw this one, K. Now, in our given, we're told that the three parallel lines split our transversal into two equal parts, excuse me. So to mark that in, I'm going to say that this length is equal to this length, and to do that you just dash once, dash twice, okay? Do one dash on each part to say that they're equal. Now labeling, I'm going to call this A, I'm going to call this B. This is where the transversal is crossing the parallel line. I'm going to call this one C, D, E, F. Okay, where the transversal T crosses parallel line L is A, where the transversal K crosses parallel line M is D, right? That's what those markings mean. Okay, the next thing I'm going to do, I'm going to take my ruler, I'm going to take my set square, And again, I'm going to draw a parallel line. I can't pick up my set square, hold on. A parallel line to T, okay? But this parallel line has to go through the point D, very importantly, okay? So it's a parallel line to T that goes through the point D. So let's do the same thing again, a parallel line. I'm going to line my set square up exactly with my line. I'm going to put my ruler next to it. And I'm going to run my set square down until it reaches the point D. Okay. All the way down. Like there. Right, see the way it crosses through the point D now? So that's where I'm going to draw my line. Now I'm going to do, this time guys, I'm going to do a dotted line through this point, okay? When you're drawing this, I'd like you to do a dotted line through this point. Now I'm going to extend it up just a little bit. My set square wasn't quite long enough. Grand. Now, so this is a parallel line to T through the point D. And again, I'm going to just label where it crosses each of the lines. So this line crosses the line L at X, and it crosses the line N at Y. And there you have it. There's your construction. The structure of this proof is split into 4 parts like many others. Okay, so it's split into our given part, our to prove, construction, and proof. So much so that if you're asked to prove something like this in the Leaving Cert, you're going to end up with this in your exam paper. Okay, a given, to prove, construction, proof. Now, what is this given part even talking about? Okay, the given is giving context to the world that we're proving this thing in. And without our context, it all loses meaning very, very quickly, okay? So I'm saying, given this scenario, I want to prove this, okay? And let me show you just in a very silly, simple example why this is so necessary. So let's say I said, given I go to the shop every Wednesday, right? I go to the shop on Wednesdays, every Wednesday, whatever. I now want to prove that there are always 3 people working when I'm there, okay? My construction might be some picture of the shop with 3 people in it, whatever, and then we have our mathematical proof. So I'm saying, given I go to the shop every Wednesday, I want to prove there are always 3 people working. Now let's say I get rid of that given part. I got rid of my contextual part. And I just say, I want to prove there are always 3 people working. Well, it's like when, where, 3 people in the world working? Well, that's definitely not true. So once I lose my given, once I lose my context, my scenario, the proof stops making sense. So that's a really, really, really important part of the proof, okay? That's why we split it into these parts. Okay, so let's set up our proof. So, given 3 parallel lines, L, M, and N, intersecting, crossing, transversal T, transversal a line that's crossing, transversal T, at the points A, C, and E. So we've got 3 parallel lines. Our transversal T is our blue line here, crossing at the points A, C, and E. Okay, such that distance AC is equal to distance CE. Okay, so it's exactly what we're setting up. We're setting up a situation where we've got 3 parallel lines, a line crossing it, and that the 3 parallel lines split that line into equal segments. That AC, this distance between A and C, is equal to the distance between C and E. Okay. We also have another transversal, another line, K, transversal K, blue line here, which intersects the lines at the point B, D, and F. We've got one transversal, one line which gets split equally into two different segments by the parallel lines, and now we've got another line going through. And what we're trying to prove is that this other line K is also split into equal segments. So what do you think we're going to write down for it to prove? Well, all we're going to say is that we're trying to prove that the distance between B and D is equal to the distance between D and F. So we're trying to prove that BD is equal to DF. Okay, perfect. Now for our construction part, okay, so I mean, we need to construct this whole thing, right? But in this scenario of this proof, we're saying that we're looking at this situation where we have everything here minus our dotted line. And now we're going to write down that what we need to construct is just this dotted line here, okay? So our construction is going to be through, that's a terrible way to spell through, let's try that again. Through D, so through the point D, draw a line parallel to the line T, intersecting L at X and N at Y. So through the point D, which we've already done, draw a line which is parallel to T. See, these two lines are parallel to each other, parallel to T, such that it crosses the line L at X and N at Y. Now we're finally ready to do our proof. Okay, we have that AC DX and CEYD are parallelograms. Have a look here, guys. ACDX, see how that forms a parallelogram, and CEYD also forms a parallelogram. Okay, and because of this, this implies, this symbol means this implies that AC is equal to XD, the distance between AC is equal to the distance between X and D, and that CE is equal to DY. Let me just take a little moment to convince you of that, okay? Just imagine these are our two parallelograms here, right? Here's one, A, C, D, X. Here's the other, C, E, Y, D. Now guys, sides that are opposite each other in a parallelogram are always equal to each other, okay? So that this side is going to equal this side, and this side is going to equal this side. Similarly, this side equals this side equals this side, okay? But all we care about here is the red sides. So we see that AC is equal to XD, and that CE is equal to DY, okay? And that's what we've just used that fact there to show that those are equal. Okay. Now if I can get rid of this. Okay. So just to mark in, right, for the reader or for the examiner, if whoever's looking at your proof, we can't just say a statement, we also have to tell them why it's true. So underneath that, I like to write in a different color pen to make it very clear, this is due to opposite sides. Okay, I write down my fact and I state why it's true. Okay, the next thing is that, however, or but, AC is equal to CE. Okay, AC is equal to CE, that was in our given. So that there must imply that XD is equal to DY. If AC is equal to CE, and AC is equal to XD and CE is equal to DY, then XD must equal DY as well. Okay. Now, let's now draw our attention to the following, okay? We have a triangle here, BDX forms a triangle. We can also see that YDF also forms a triangle, okay? So, in the triangles, BDX and YDF, let's observe the following. We have that the distance XD is equal to the distance DY. XD is equal to DY. We already figured that out from before. Okay, that's the last thing that we showed. We also have that the angle BDX is equal to the angle YDF. Okay, the angle BDX here is equal to the angle YDF here. Why is that, guys? It's because of opposite angles. They're vertically opposite each other. Okay, vertically opposite angles to each other are always equal to each other. So off we go. We can write that in. That this is because of vertically opposite angles. They're vertically opposite, guys. Again, I'm writing in my reasoning in other pens to make it very, very clear to the examiner or to whoever's reading my proof why this is true. The next thing I have is that the angles DBX is equal to the angle DFY. Let's have a look. DBX, this angle, is equal to the angle DFY, this angle. And why are these angles equal to each other, guys? Because they are alternate angles. They are alternate angles. So what do we have here? We have these two triangles have this angle equal to each other. They also have this angle is equal to each other. And not only that, they have a common side. They also have a side that's equal to each other. What happens, guys, if you've got two angles equal to each other and a side equal to each other in two triangles? That means that they're congruent triangles. That means these triangles are identical. Okay. So this implies the triangles BDX and YDF are congruent. The same, basically, is what that means. Now, if these angles are the same, this implies the side BD equals DF because they are corresponding sides in the triangle. They are corresponding sides. Again, writing my reasoning in another color to make it really obvious. Corresponding sides. Let's have a look. So the angle, the distance BD and DF, do you see the way they are? These are both in between this green and red angle in both these triangles. So therefore they must be the same. They must be the corresponding sides to each other. And if those sides correspond to each other in a congruent triangle, two triangles are the same, they must be equal to each other. And guys, there you have it. You finished your proof.